Hello everybody, today we're going to be looking at quadratic regressions. The goal today is going to be to be able to write a quadratic equation without the vertex. Right? That's going to be our goal today. We use this method when we are given a data set. Right? We use this method when we are given a data set. And it's going to require the use of our friend Desmos. So you're going to need to use Desmos to do this. Okay? We use this when what we call the second differences are either close or exact. So the second differences is when you have a data table. And I'm just going to make one up real quick. I have X and Y. And let's say it's like 2, 4, 3, 9, 4, 16. I'm doing this on purpose to be quadratic. It's when the second difference, well, the first difference is what we need to calculate first, okay? So what we do is we take each pair and we subtract them. So 4 minus 9 is 5, 16 minus 9 is 7, 25 minus 16 is 9, and then we subtract again. And do you see how we got 2 both times? And if I kept going, I would get 2 the whole time. This is telling us the exponent. So because it's the second degree out, we had the first difference and then the second difference. Because it's the second difference, that tells me that my exponent of my equation is 2. So when the second differences of our data table are close or exact, we use this method. We're going to get something called an R squared value, right? The R squared value is going to want to be either close to -1 or 1. If it's close to 0, it means that the data is not very quadratic, okay? All right, so to do this, I have Desmos pulled up on my iPad. So what I'm going to do is I'm going to pull this up, and I'm just going to plop Desmos right over here. Okay, obviously it's going to look a little bit different for you on your computer, but I'm going to plop it right up here. So, and I think if I play this right, I can even, wait, hold on. Wait, okay. I'll edit this. Maybe I won't. We'll see what I can manage to do. All right. So, the first thing we want to do is click on the little plus symbol. And we're going to add a table because we have this table right here, okay? This table right here, we're going to add it. So now I just type in the data. So my data is 10. Oh, I got to make sure I'm clicked in. It's 10. Then it's 15, 20, 25, 30, 35, 40, all right? Then I'm going to enter in my Y values. So 26,900, 29,025, 30,600, 31,625, 32,100, 32,025, 31,400. And we can kind of see that the graph, like that these data points, they start off in the 26,000s, they go up, 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 and we get up to 32,025, and then we go down to 31,400. So it's definitely having that parabola shape. Okay, so I entered the data into the table, and you'll notice that it called the data x1 and y1. So what I'm going to do is I'm going to say y1, and I got that by just saying, typing in y and then the number 1. If you type a number right after a variable, it does that for you. It makes it a subscript. Not equals, excuse me. And we use this little squiggly. It's right next to the 1 key or above the 1 key, depending on your keyboard. And you just have to hit shift to get it. You want that little squiggly. And then we're going to type in ax1 squared, all right? You can either use like that shift 6 trick or the little exponent button in the bottom, plus bx1 plus c, okay? And it tells us some stuff. So let's just read the problem real quick. So NASA can create a weightless environment by flying a plane in parabolic paths. The table shows the height h in feet of a plane t seconds after starting the flight path. After about 20.8 seconds, the passengers begin to experience a weightless environment. Write and evaluate a function to approximate the height at which this occurs. So what we did by entering this data into Desmos and then having it write an equation for us is we said, and it told us, you'll see, it says A equals B equals and C equals. So we got that y equals negative 11x squared plus 700x plus 21,000. And my r squared value equaled 1. That tells me that it's a perfect fit. All right? So now I'm going to zoom out, and I think it's just important for us to see this equation. And it's going to be hard for me to get the right window when I'm sharing my screen like this, but you can see that it's a really thin parabola. But you can see it goes up, and it graphed my data points too, and you can see that it goes right through all my data points that I graphed. I'm going to tap off them now. But it says, after about 20.8 seconds, passengers begin to experience a weightless environment. I want to write and evaluate a function to find the height at which this occurs. Okay, so now 20.8 seconds is an x value. So I'm just going to plug that in for x and solve. You can use the calculator here, or we can do it by hand. I recommend using the calculator, obviously. I mean, you're definitely going to want to do that too. I don't think you know what 20.8 times 700 is off the top of your head. I don't. So all I'm going to do is negative 11 times 20.8 squared plus 700 times 20.8 plus 21,000. And I'm just going to type that in. In the graphing calculator on Desmos, you can literally type in like this, like negative 11 times 20.8, and then you can square it. Then you can add 700 times 20.8 plus, close the parentheses, plus 21,000. And that tells me 30,800.96. All right, so the weightless environment occurs at 30,800.96 feet. All right. We have two more examples in here. I'm going to do the second one with you, and I want you to try this third one on your own. But let's go ahead and try this one out. So this one, the table shows the fuel efficiencies of a vehicle at different speeds. We want to write the function that models the data and then use the model to approximate the optimal driving speed. All right, so I'm going to need new data, so I'm just going to get rid of all my stuff. I'm going to hit the little home button on Desmos so it resets my screen. I'm going to add a new table in. And so I have 20. Just edited that part out of me entering the data. That's kind of, I assume you can do that. And one thing I want you to always do is if your answer starts to look really out of whack, like let's say you got some ridiculous driving speed for this question, double check and make sure you typed in all your data correctly, okay? Make sure that you didn't like make a typo somewhere. So y1 squiggly. All right, I'm just gonna kind of zoom out so I can see what's going on here. I think it's always good to just kind of give yourself the picture. All right. We don't need to like be super exact in our graph, but it's just nice to have it. It's y equals negative 0.014 x squared, I'm going to round, plus 1.366x minus 7.144. All right. My r squared equals 0.999. It's a very good fit. So we can kind of rely on this data, on this model to make predictions. So what we're looking for is the optimal driving speed. I mean, how many, we want a speed that's going to maximize the miles per gallon I get, my fuel efficiency. Now, I'm going to turn my data points off for a second. You can do that just by clicking or tapping on, see on next to Y1. I can just do that. Now I just see my curve. When I touch my curve, you'll notice that it highlights some key points that we've been talking about, right? It highlights the y-intercept, it highlights the x-intercepts, and the vertex. If I'm looking for the optimal driving speed, the best driving speed, that refers to the vertex. If it was asking me for where something was equal to 0 or where it lands, I would look at x-intercepts. And if I was looking for something where something starts, I might look at y-intercepts. But because it's asking me for the maximum, the best, the optimal, I'm looking at the vertex, which is 48.457, comma, 25.957. Right? I want the driving speed, so that is the x value. So the optimal driving speed is 48.457 miles per hour. Right? I would like you guys to try this last example. Make sure you're able to do this. It says using your TI-84. Using Desmos, okay. Try this out. You're going to need the practice, okay? And there you go. Have a good one, guys.